the frame from the video, film the audience, the artist, or anything. So the challenges involved with designing such a system are first the need for a CPU, because MilkDrop overall is a very complex system, and if I were to implement everything in hardware without any software, it would get horribly complicated and not even efficient, because I would need many big state machines, which would fill up my entire FPGA and which would be awful to program. So it definitely needs a CPU for taking care of the software-friendly tasks like the GUI interface, field file system, protocols, all the housekeeping of running the graphical pipeline. And it also brings out some flexibility, ease of programming, and also you can easily patch software bugs without recompiling the whole FPGA design. The other challenge is even though the FPGAs are getting cheaper, you still have to be very careful because they are not so cheap. So you have to make a very careful design and strike a good balance between hardware and software to get the best compromise between speed, size, and cost. Basically, software is cheap and slow, and hardware is expensive and fast. So you have to balance and choose what to put in software and what to put in hardware. You have a big problem that I had, it took me 1 year to solve, are the memory problems. Because you need a lot of memory bandwidth to take care of the video, and you also need a lot of memory to store the frame buffer, the textures, and everything. And the only technology which is capable of doing it is DRAM. And DRAM is very hard to take care of, especially at high bandwidth. And finally, you have compute-intensive operations. For example, distorting the image and evaluating the equations need a lot of processing power that you cannot really do on the CPU. So the architecture that I have chosen is a system on programmable chip. So a microcontroller, a bit like AVR, but a bit more powerful, is implemented in the FPGA fabric. So microcontroller is a CPU plus some additional peripherals, like UART, like GPIO, video frame buffer, all this. Then you write software and compile it with GCC, for example. And the processor that I'm using is Lattice Micro32, is supported by GCC. Even the patch is included in the newest GCC. So you compile it with GCC, you load it into the board, and then the microprocessor made from the FPGA fabric will execute your software. And from your software, you can drive an acceleration unit and special peripherals that you add into the FPGA fabric and drive them with the software. So now, as I said, I will start with studying some cases. And first, as I said, the memory problem is a very tough one. So I will a bit explain how you could solve it. So the application requires memory to be big. You need a lot of memory for textures, frame buffer, all the like. Fast and cheap, because I want the device to be accessible to most people. And the required memory size prohibits the use of SRAM, because a very easy memory technology to use is SRAM, stands for static RAM. But if you need a big memory size, SRAM gets extremely expensive. For example, if you buy a 4 megabyte chip of SRAM, it will cost like 100 euro or something, so that's out of the question. So I have to use DRAM, like in computers, for example. You know, SDRAM, DDR SDRAM, DDR2 SDRAM. This is the type of memory that I have to use because of the cost constraint. And this memory is very hard to drive. So first, I will just see how much memory I need, how I can do it. So we'll draw the table of the memory bandwidth usage and memory capacity usage. So first, what I need in my system is a VGA frame buffer running at a nice resolution. And if you do the math, this resolution requires nearly 1 gigabit of memory bandwidth, approximately 2 megabytes of size. Distorting the image is also a big memory bandwidth consumer. You need 700 megabytes per second. Then, as I said, I needed also video inputs. They don't use so much bandwidth because NTSC or PAL video is not so high resolution and not so high frame rate. So it doesn't eat up so much bandwidth. And finally, for software, for example, the graphical user interface, for the UART, for whatever, the sound I/O, for example, you need roughly 250 megabits per second. So if you sum up all this, you see that the memory chip must have a sustained bandwidth of 2.2 gigabits per second, So between the FPGA or the custom chip, if you want to make one, you will have a continuous flow of data, which amounts to 2.2 gigabits per second, and the total capacity of the memory is approximately 22 megabytes. That's only the basic system that you will need. So let's see what the memory market has to offer. If you take, for example, the DDR SDRAM, which is commonly found in computers, most laptops use it. Now they are more using DDR2, but it's very similar. If you run it at 100 megahertz, it can give a peak bandwidth of 3 gigabits, and it can have a 32 megabytes capacity, and it costs a few dollars. As you can, when you buy your memory for your computer, you can see that it's very cheap, especially if you need only 22 megabytes. Today's chip take hundreds of megabytes and are not expensive. So, well, it looks like still manageable. But there is one thing that is a big problem. It's 3 gigabytes is a peak bandwidth. This is a big problem because, as you will see, the performance of CSDRAM depends a lot on the cleverness of the controller. For example, I will just give one of the examples, which is easy to understand, to explain how you can get the most bandwidth out of a memory chip. For example, if you have a very simple SDRAM controller, you issue a read first here, and then you wait for the data, then you continue your execution, and you need another word to be taken. So you need another read command, and then the data has to come a few clock cycles later. And well, you can see it takes a lot of time if you wait for the data before issuing the next command. If you have a more intelligent SDRAM controller, you can issue a read command every cycle, and then the memory will give the data with a bit of latency a few cycles later. And you can see that if you optimize the SDRAM controller, the memory access time will really shrink, and you can really use 100% of the bandwidth, because if you keep the figures that I gave, which is 3 gigabytes for a DDR200 chip, is when every slot is taken here. But to take every slot, you need to issue also a read command at every slot. And so you need to predict perfectly the address sequence that you put into the SDRAM. And on top of that, you have other problems like memory refresh, or sometimes you have to change rows in the DRAM array. But well, these are more technical points that I'm not going to cover today. I will just explain this. So if you want to predict the address sequence, it's hard, because typically if you have, for example, a for loop, the CPU must be able to do some kind of speculative execution, or to things that the program, if you have, for example, a for loop, if you want to copy two buffers, for example, if you load one word and then store it in the next, you have to reorder the instruction in order to be able to continue execution, even if the memory has not given you the data. But you need to continue execution to compute the next address, and that's pretty hard to do in software. But what you can do, which is a much simpler solution, which doesn't need an out-of-order CPU, is do something which is called bursting. Every time you do a memory transfer, you get the first read command, and then you read the consecutive words. And in Milkymist, I am using a burst of 4 words. So every time I request any word from the memory, the controller automatically requests the next 3 words. And I will then discuss how it could work, because it may seem a bit strange to do that, because you're not even sure if you're reading the next word or not. But I will then discuss that. So let's see if it's a good idea. Well, is it good for the VGA frame buffer, for example? Well, the VGA frame buffer, as you have seen from the table before, is a big bandwidth consumer. So let's see how we can do that with it. So every time it gets a burst of 4 consecutive chunks from the memory, these chunks they also represent consecutive pixels in the screen scan order. So when you get the burst of 4, you just put them into the FIFO, and then you can slice it every time the screen needs a pixel, and you achieve 100% bandwidth utilization. So it's perfect. For the PAL and TSC video inputs, it's exactly the same problem. Only you're not reading, you're writing. You're just getting data from the video input. You put it into a buffer, and when the buffer is full, which means it contains 4 memory words, you just put them into the memory controller in a burst, and you also achieve 100% utilization. Is it good for distorting the image? Well, yes, it's good. I will explain it later. So it seems a bit strange, because you can see the image needs to read pixel in if you are distorting an image, you need to read pixels in strange orders, but you have a way around it, and I will explain how.